Welcome and thanks for joining us. I'm Linda Bell, Editorial Director at TechBriefs Media Group, and I'll be your moderator for today's webcast, Advantages of Smart Servo Steppers versus Smart Brushless Servos, sponsored by Nanotech. Today's webcast will last about 30 minutes, and there will be a question and answer period at the end of the presentation. You can submit a question anytime by entering it in the box at the bottom of your screen. Our presenter will answer as many questions as possible following the presentation, and those questions not answered during the live event will be addressed following the webinar. In order to view the presentation properly, please disable any pop-up blockers you might have on your browser. Now let's meet our speaker. Mike McShane is Sales Manager for Nanotech Electronic US and has been in the motion control industry for 30 years. He has experience with smart servos, servo drives, brushless servos, actuators, steppers, linear servos, and gearboxes. Now I'd like to hand the program over to Mike McShane. Mike?
Thank you, Linda. All right, thanks everyone for joining us. Today we're going to get into in-depth the differences between smart servo steppers and smart brushless servos. And by the end of this, I'm hoping that you all walk away with the understanding of where does each fit, and more importantly, how is that advantage, how does, the advantage to you on the specifics of each technology. Okay, so we're going to do a quick outline here. We're going to do installation advantages. We're going to get into technology advantages, disadvantages, and applications of each, and then wrap it up with some application examples at the end. All right, so smart servo advantages. These are pretty straightforward. We're eliminating components inside of electrical panels, eliminating wiring going from the motors to the electrical panels. That all saves cost. We are adding power supplies into the panels, so not a complete elimination. Also, smart servos cost less than AC servos, so there's a lot of savings to be had. Real quickly, I wanted to just briefly cover motor technology from just the advancements that have been made. I didn't want to get into a big, long dissertation on it, but motors have been improving. I mean, in the last couple of years, every step motor manufacturer has gone through a redesign and come out with higher torque stepping motors, and the same holds true for brushless. The biggest advancement in brushless was the segmented windings, where you get more copper into the same size motor, i.e. more torque, higher performance. All of these advancements make smart servos even better. All right, specifically, we're going to start looking at smart servo steppers. From the technology standpoint, we're taking a two-phase standard hybrid step motor, 1.8-degree step motor. We're doing field-oriented control, basically vector drive. So we're adding a single-turn absolute encoder on the back. I think this is standard across the industry. The single-turn encoder gives us rotor position as well as encoder. So rotor position can be obtained with Halls or a single-turn absolute encoder. So on power up, we know exactly where the rotor is and can commutate it on power up. So a complete servo system in one compact package. Looking at steppers, stepping motors historically have had very high safety margins because when you look at a torque speed curve, that line is the stall line. Now, when you servo the step motor, that line is now the continuous line. So in the past, if you touch that line, the motor would freeze in its tracks. We don't have that problem when we're servoing the step motor. We're eliminating noise, vibration. Improved accuracy is a big one. A step motor has the accuracy of 5% of 1.8 degrees, where now we're the accuracy of the encoder, so much higher count, much higher accuracy. Okay, so looking at what are some advantages, probably the number one that I left off here is compact size. But when you look at stepping motors versus brushless motors, stepping motors have 3 times the continuous torque of a brushless motor. But you can see here from this curve that the brushless motor can really do anything that a stepping motor can do because of the peak torque of the brushless motor. So why does a servo stepper make sense? Now, first of all, 20-to-1 inertia mismatch. That's for positioning applications. With feed-forward loop adjustment for velocity applications, you can get all the way up to 100-to-1 inertia mismatch. So we can direct drive applications that you would need a brushless motor and gearbox for. So that's one big advantage there. Another one is power requirement. These are both, when you look at this torque speed curve here, these are both NEMA 23 motors. The Smart Servo Stepper needs 4.2 amps, 24 or 48 volts. The Smart Brushless Servo needs 18 amps, 48 volts in order to do the same motion. Big cost differential there on the power supplies. So you can see the advantage of a servo stepper if it fits into your application. All right, some disadvantages: low speed smoothness. You know, when you get down under 20 RPM, you're starting to get down to the point where your velocity isn't fast enough, and you can start seeing the encoder resolution coming out. It's just the nature of the beast. V10 torque, it's a stepping motor, so it's going to have torque ripple because of the V10 torque. Instability at the curve, or at the knee, so the curve down in the torque speed curve. There is instability at that point because you're changing the load angle, and so it takes a little bit of time to get the load angle correct, and there is some instability in that zone. You know, we've got some, you know, when you look out across the industry, there's some manufacturers out there that sell brushless, smart brushless servos for replacing stepping motors. You can see here the advantage of using the smart brushless servo, the smart servo stepper instead, because of the lower amperage and lower cost. So on this one, I wanted to cover just the size ranges. I want you to kind of focus on really just the torque and the amperage required. So NEMA 17 to 34. 70 ounce-inches of torque on the 17, 1.8 amps, 24 volts is what it takes to deliver that. On the NEMA 34, 1,300 ounce-inches of torque, 9.5 amps. You know, that's a lot of torque out of a NEMA 34 package. Again, out of a 24-volt power supply as well. All right, taking a look at some applications. Peristaltic pumps is a huge one. We get into a lot of peristaltic pump applications, wheel drive applications, gantry systems. You know, general automation covers a ton of stuff. Let's take a look at gantries for a minute here. So all of these applications, if you remove the tool off of it, you couldn't tell what the machine does. So an H gantry, dual X, Y, and a Z, and then you either put a laser cutter on it, a router, or whatever, and you've got your machine. So these are all pretty much the exact same, and we see a lot of these. Labeling. The first labeling application I did, the labeling company was running a dancer arm, 2 sensors, and a potentiometer, typical dancer setup. We were able to eliminate the dancer arm, and we direct drove it with a 60 millimeter of the NEMA 24 servo stepper, put it in torque mode, and eliminated all of those components, saving them money. And so it just sits there, applying force, waiting for a label to print, and then takes up the slack. You know, since then we've gotten into, you know, driving pinch rolls. I can tell this is a bottling line when you see the top trap conveyor. That conveyor needs to exactly match the speed of the conveyor below. So all of those things we've done, and Smart Servo Steppers shine in these applications. Here's one of our European customers. They're making a 5-axis machine for psoriasis treatment. So at this point, we're going to stop for just a minute here and watch a video. I want you to listen to the motors. And when we come back, we're going to start getting into smart brushless servos. But we're going to start the video now.
For We're showing 3 NEMA 17 Smart Servo Steppers. We're doing coordinated motion over CAN open without a PLC. It's done with a 1 millisecond update time. Motor number 1, the white gear, is acting as the master. Motor number 2, the orange gear, is doing one-to-one gearing. Motor number 3, driving the ball screw, is being commanded by motor number 1. Total system cost here is under $1,000.
All right, thank you. So we're going to get into had to get to the next slide. So smart brushless servos. Technology-wise, we're looking at exactly the same thing, except we've got a 3-phase brushless motor. Everything else remains the same between the Smart Servo Stepper and the Smart Brushless motor. So again, the same torque speed curve. Couple of things that we have to live with: 10-to-1 inertia mismatch. All right, it is a compact size. You know, probably one of the things I should have said for both of these is that, you know, in the past, you go back 10 years or longer, the electronics generated heat, and so putting electronics on the back of a motor, they generated heat, the motor generates heat, was a terrible solution and greatly limited the performance of what you could get out of smart servos. But in today's day and age, you know, it's a little unusual to even see heat sinks, except on some of the really larger ones. You know, a lot of them don't even have any heat sinks anymore because the electronics don't generate the heat. And so all of that adds to compact size. And, you know, getting back to, you know, the torque speed curve here again, I showed you that a brushless servo can do anything a servo stepper can do, plus wider speed range. So even if your application was, you know, 400 or 500 RPM, if you needed that peak torque, the torque speed curve on a servo stepper is going to cut right down through there and be too close. So, you know, anything beyond that line in any way is going to drive you to a servo stepper. So the disadvantage is pretty much the same of, you know, if you slow down too much, you've got the encoder resolution coming out, you know, below 20 RPM. The amperage required is a huge thing. And so let's take a look at that. You know, when we look at the speed ranges, the NEMA 17, you know, motor, that means 48 volts, 10 amps to drive it. NEMA 23, we've got 24 and 48 volt motors. I'm assuming the rest of the industry does as well, and there's other voltages out there as well. But, you know, up to 18 amps peak on a NEMA 23. NEMA 34 and 80 millimeter, this is where we get to some really high amperage. So the 80 millimeter, 940 watts is kind of the biggest we see in the industry now. And we've just introduced one ourselves, and that needs 25 amps, 85 peak. So as you can imagine, 85 amp, 48 volt power supply, at that point, it's probably 150, 160% the cost of an AC servo. Well, we do have customers using them to replace AC servos because some customers want to build machines where they sell them around the world and they don't worry about UL and things like that. But for the most part, most of those high amperage applications get into battery operated. Moving on. And so for applications, really the applications are all the same. It's really all, you know, speed torque curve driven on which one you choose. You know, so I think the only one I removed, which I thought of recently that I shouldn't have removed, is peristaltic pumps. I thought of it recently with a big customer that buys smart brushless servos from us with gearboxes and is doing peristaltic pumps. But for the most part, those are direct driven with servo steppers. All right, some battery-operated applications. So robotic wheel drives, lifts, arms, etc. The picture below is a product that we actually manufacture, so a complete wheel drive assembly. We put one of our Smart Servos on it and deliver it as an assembled package. Typically, those are all these robots typically run can open. It's very unusual where they're not running can open. The picture on the right is a customer of ours, and they make a really cool robot. They're doing mecanum wheels, and they've got a robot that carries 500 pounds and a robot that carries 3,000 pounds with all mecanum wheels. And so if you're standing in the way, the robot will literally come to you, drift to the side, and go around you. It's really cool. All right, so some side-by-side comparisons here. So, looking again, what are the advantages of each? Obviously, speed. For the Smart Brushless Servos, speed has it. That wins every time. Inertia mismatch on the Smart Servo Steppers, 20 to 1, all the way up to 100 to 1 in some applications. The disadvantage on both, low speed smoothness, that you have a certain speed range because of the encoder resolution on the motor. So kind of under 20 RPM, you can get to a point where you will see that dropping out. Amperage advantage of the Smart Servo Stepper is a big advantage and a big driver. All right, so I wanted to deviate here for just a second and talk about Nanotech, because we have solved some of the disadvantages on the Smart Servo Steppers. So the slow speed smoothness, we invented a new slow speed mode that eliminates that smoothness issue. And so it's a really cool invention that we came up with. And this is our third generation of products. We've been doing servo steppers and brushless servos for over 10 years now. And we've eliminated, on the servo stepper, we've eliminated the instability at the knee or the turn down in the curve. And so that, again, is something that's actually new for us in the latest generation. But because of our experience, we've been doing this the longest. Most of our competitors have really only been around for the last 2.5, 3 years. And so that's a big advantage that we have as well. Another thing as far as that goes, sorry to kind of pause and come back at it, but we've got competitors that are also selling drives and motors with encoders separately. And there's a couple of manufacturers out there that can't even get past that stability point or the instability point on the curve. And so that's a big advantage that we have. One of the things that we do is we combine programmability, step and direction, analog in all into one unit, reduce our part number count, and try and drive the volume up so we can drive the cost down. For whatever reason, most of our competitors sell step and direction as their lowest cost unit, and then if you want it to be programmable or something else, that price goes up dramatically. So that's something to pay attention to when you're shopping around, is what do you really need and what is truly your cost. We use standard industrial connectors, so M12, M8, and Phoenix. So we're using low cost, readily available, connectors, and you will find that some use more exotic connectors that are much more expensive. All right, let's get off Nanotech and get back into some applications here. So from a couple of application standpoint, now we're just going to focus on just speed and torque. We're not going to get into inertia, so just basic information here. So 280 RPM, 56 ounce-inches of torque. What can we solve it with? So a NEMA 17 brushless servo with a 9-to-1 gearbox. It's an economy gearbox, and we're looking at $576 to solve this. We need a 48-volt, 10-amp power supply. We could also direct drive it with a NEMA 17 Smart Servo Stepper. We're looking at $323, 24 volts, 2 amps. Hands down, Servo Stepper wins. Next application, 500 RPMs, 400 ounce-inches of torque. A NEMA 23 Smart Brushless Servo with a 5-to-1 gearbox. This happens to be a 24-volt motor, needs 20 amps of power, $597. We could direct drive it with a big NEMA 34 Servo Stepper, $554, needs 48 volts, 10 amps. This is a coin toss. I think size takes it every time. But some of you may be looking at it going, no, I'll take the Servo Stepper instead of the brushless. Like I said, it's a coin toss, but I think smaller is always better. All right, last application we're going to look at, 20 RPM, 8 Newton meters of torque, 1,100 ounce-inches. So a NEMA 17 Smart Brushless with a 100-to-1 gearbox, we're looking at $757 for it. It needs 48 volts, 10 amps. We could also do it with a NEMA 17 Smart Servo Stepper with a 40-to-1 gearbox. $651, needs 48 volts, 2 amps. So in this case, the Servo Stepper, I think, takes it hands down. It's better cost savings all the way around. All right, we're going to jump into some questions. If you guys have any questions after this, please feel free to send us an email at info@nanotech, info@us.nanotech.com. It's on our website. Label the subject of the question as just webinar question, and we will get it answered. Linda, first question.
Great. Thanks, Mike. The first question we have is, what is the difference between closed-loop microstepping and closed-loop servo?
Okay, great question. So closed-loop microstepping, a lot of people have heard and seen marketing where people are saying, no hunting, no hunting really is kind of the big one they advertise. So there are some manufacturers out there that have taken the approach of taking microstepping with encoder feedback and wrapping a servo loop around stall detection and then do error correction if they lose position. We feel that servoing is better because when you servo the motor, you're actually quieting the motor down, you're eliminating vibration, and so that's the route we've taken. They're both good solutions, but one is keeping all the negatives of a stepping motor, noise and vibration, and then doing error correction with an encoder versus true servo.
Okay, let's see. Next question is, so a Smart Servo Stepper would not be recommended for a low-speed application?
We'd have to actually take a look at that application because a real low-speed application, we have the new low-speed mode that we could very well drive it with our low-speed mode. But if for some reason, let's say that somebody wanted to do, I don't know, I'm trying to think of a number. If you wanted to do like 0.1 RPM a minute, and if our slow speed mode didn't solve that, then we might want to go to, a very high resolution gearbox to speed the motor up. But in that situation, yeah, a servo stepper would probably still be the lowest cost solution.
Great. Is there a way to electronically measure the torque required while the motor is turning?
Yes, we have. We and I think everybody else, when you're servoing a motor, you can take a look at the amperage that's being delivered, and then you could calculate right in the motor how much torque you're actually generating, or take it back to a PLC and calculate it.
Okay. Let's see. Do you offer Profibus field bus?
Somebody would have to ask that question. We are a German company, and we do not offer Profibus at this point. It is on the schedule, but as of today, no.
Okay. Let's see. How do you tell the motor basically what to do?
Okay, so we have what we call our plug-and-drive studio, and we're actually about to release a new plug-and drive studio. Currently, we've got programming examples that you can copy in and modify. It is true programming, and that's what we are going to be eliminating this summer with our new plug-and drive studio, to have simplified programming where you can say that, hey, I want to move, put in a distance. I want to move from here to there with an input, and very simplistic programming is what's coming. But currently it is actual coding that does it. But we do have quite a few example programs, and Lincoln Noggle is on the phone daily helping people out with these types of issues and getting them up and running.
Okay. What happens when a motor is back-driven?
Okay, so smart servos, whether they're steppers or brushless, will generate power back onto the power supply when the motor is back-driven. So in an application like a feed out for, say, labeling, or robotic, if you're going outside and you're going to drive it down a long hill, something like that, it's going to generate power that needs to be dealt with. Now, some power supplies can deal with it for short periods of time. I mean, in very short periods of time, there is capacitor, but that power generation typically needs to be dealt with and bled off onto a resistor bank that's going to generate heat in its place.
Okay. Let's see. Do you have Rockwell AOPs?
So we actually, on the Rockwell side of things, we actually just went through, and whoever asked that question will get you a better answer. Lincoln Noggle just headed up a team to improve our Rockwell experience, and our capabilities of our motors are vast, and with Rockwell, it's fairly narrow, and so I'm trying to explain it as simply as possible. But we have all sorts of things like synchronous. If you're trying to do coordinated motion, and we don't have any coordinated motion with Rockwell, so Lincoln essentially took that out, simplified everything so that it's a much easier experience. I think the answer to the question is yes, or they are almost developed. I'm not sure which, but we did have them, but they were very complex. And so far, the feedback I'm getting from customers is 2 thumbs up. It's much better.
Okay. Let's see. What software is used to program the servos?
So we have free software on our website that's Plug and Drive Studio. It programs all of our products, and so it's free on our website. It is, as I said, coding. It is C++ programming, but we do have, not to scare anybody, we do have example code that you can copy in and be up and running in minutes.
Great. We have time for one more question here. Are motors offered in multiple communication protocols, or is it a singular protocol per part number?
So we have multiple field buses. We have CAN Open, EtherCAT, Ethernet IP, Modbus TCP, Modbus RTU, and as a German company, we don't have Profinet. Or Profinet, Profibus, whatever it is, the Siemens protocol.
Okay.
But yes, we do have a wide variety.
Great. All right. Thanks, Mike. I would like to thank our speaker, Mike McShane, and all of our audience members for attending today. And just a reminder that the webcast will be available on demand for 12 months at www.techbriefs.com. Thanks again, and have a great day.